The coral reefs knew first. For months, marine biologists studying Simului Island's fringing reefs had been documenting strange vertical movements, microscopic uplifts that made no sense. On November 27th, a magnitude 6.6 earthquake confirmed what the corals had been recording. The Sunda Megathrust was stirring after 267 years of silence. These were not random oceanic shifts. They were systematic preparation signals from a fault zone that last ruptured in 1757, generating tsunamis that killed thousands of us across the Indian Ocean. What makes this reactivation absolutely terrifying is recent scientific discoveries revealing the Sunda system's true nature. Not just a fault line, but a 5,500-kilometer cascade network operating like a planetary earthquake machine. Research in 2025 exposed the systematic threat we have been ignoring. The Sunda Megathrust exhibits coordinated failure patterns where ruptures cascade across segments in planned sequences. Historical coral records document this exact pattern during the 17th century, 5 major earthquakes over decades, each preparing the network for systematic regional collapse. Now, probability models confirm the 267-year accumulation cycle is approaching critical release. The same fault network responsible for the deadliest tsunami in human history is showing systematic activation across multiple segments. What the coral reefs detected first, microscopic movements that preceded cascade failure, suggests the countdown has already begun. If nature's most sensitive geological sensors are confirming megathrust activation after 267 years, are we witnessing the opening sequence of the largest earthquake cascade in recorded history? When a fault network capable of 30-meter tsunamis begins its long overdue systematic failure, what happens to the 600 million people who never saw the coral warnings? On August 15th, 2024, Indonesia's Meteorology, Climatology, and Geophysical Agency, BMKG, issued a sobering clarification. The Sunda Strait and Mentawai Cyberroot zones represent seismic gaps that are hundreds of years overdue for significant releases. Emergency geological assessment teams deployed across Indonesian monitoring networks, mobilizing the nation's scientific resources to understand an unprecedented threat. That threat materialized on November 27, 2025, when a magnitude 6.6 earthquake struck the subduction zone offshore Sumatra, damaging buildings on Simului Island and confirming systematic fault activation in the exact regions identified by probability models as the highest risk. Dr. Daryono, head of the Earthquake and Tsunami Center at BMKG, described the pattern bluntly: significant seismic events due to hundreds of years of pressure accumulation. The technical data is alarming. 2024 probability models using Gutenberg Richter frequency magnitude analysis predict a major earthquake as early as 2026 to 2027, with an even more significant event estimated likely around 2031. GPS measurements confirm Java Island experiences an average plate shift of 6 centimeters per year, with earthquake supercycles occurring every 400 to 600 years. Advanced seismic monitoring techniques, like hypocenter relocation using teleseismic double difference methods, reveal a large seismic gap extending south of West Java into southeast Sumatra, a region that has been ominously silent for over 2 centuries. Computational simulations demonstrate the 3-dimensional subduction dynamics at play, where the pull of the dense Java slab drives systematic stress distribution across the entire Sunda margin. Coral microatolls provide an unprecedented level of paleoseismic precision, showing time-varying interseismic strain rates, with similar seismic ruptures recurring on identical fault patches over multiple earthquake cycles. Cutting-edge bathymetric surveys even detect divergent deformation patterns in the accretionary wedge, correlating with enhanced tsunami hazard zones. But perhaps the most alarming revelation is the fundamentally interconnected nature of the Sunda Megathrust system. Indonesia sits at the convergence of three major tectonic plates, creating a network of 16 megathrust segments across 6 active subduction zones. Earthquake cycle behavior across this system exhibits clustered complementary ruptures and rupture cascades, where segment barriers can be persistent, frequent, or ephemeral. These multi-segment rupture cascades demonstrate how a single segment failure can trigger ruptures on distant segments, as may have occurred in 1660 when a tsunami from the Banda Aceh region followed a separate rupture in the Mentawai zone. Dr. Nuraini Rahma Hanifa of Indonesia's National Research and Innovation Agency, BRIN, warned, "The energy from centuries of plate convergence can be released gradually or sporadically, and we must prepare for both possibilities." Economic estimates for an earthquake of magnitude 7.8 to 8.2 suggest potential damage up to $1.255 billion, with significant loss of life. Recent research confirms the primary control of Java slab pull driving northward, increasing oblique convergence across a dangerously systematic network. The Sunda Megathrust is a geological titan. Extending approximately 5,500 kilometers from Myanmar to Australia, this subduction zone is capable of unleashing magnitude 9.0 or greater earthquakes and tsunamis reaching 30 meters high. Located at the convergent boundary where the mighty Indo-Australian plate subducts beneath the Eurasian plate, it is one of the most seismically active structures on Earth. The megathrust is divided into distinct segments: the Andaman, Sumatran, and Javan sections, with a curvy planar geometry that increases in dip from 5 to 7 degrees near the trench to a steeper 30 degrees beneath the coastlines. Historical rupture patterns reveal the megathrust is segmented, with the largest earthquakes occurring on separate patches, offset by smaller events at the boundaries between patches. The 1797, 1833, 1861, 2004, 2005 and 2007 events delineate these distinct rupture zones. Scientists have categorized the Sunda Megathrust's normal rupture behavior into 4 patterns. First, quasi-periodic similar ruptures. Second, clustered similar ruptures. Third, clustered complementary ruptures. Fourth, superimposed earthquake cycles of different scales. The devastating 2004 Sumatra Andaman earthquake involved a 1,600 kilometer section of the fault that had lain dormant for about 1,000 years, followed by a 350 kilometer rupture beneath Simulue and Nias Islands just 3 months later. Remarkably, the 1861 event appears to have been similar in extent to the 2005 rupture, suggesting a repeating rupture pattern. The 2007 Bengkulu earthquake is interpreted as a partial failure of the 1833 rupture area. However, the Java-Bali segment appears comparatively less active, possibly due to mainly aseismic slip rather than large seismic ruptures. But it is the historical 267-year event timeline that truly stands out as an alarming systematic pattern. Historical records indicate the last major earthquake in the Sunda Strait occurred in 1757, meaning the current seismic gap now spans an incredible 267 years. For comparison, Japan's Nankai Trough, another subduction zone notorious for megathrust events, has a gap of only 78 years since its last rupture in 1946. 17th century coral and sedimentary records demonstrate a period of systematic rupture progression. 5 discrete uplift events identified around 1597, 1613, 1631, 1658, and 1703 represent large megathrust ruptures that propagated across the Mentawai segment in a cascading sequence. This series of coordinated ruptures starkly contrasts with the following supercycle culmination, which involved only 2 large ruptures in 1797 and 1833, suggesting variable patterns of segmented failure progression. The systematic nature of these failure cycles becomes evident through advanced coral microatoll analysis techniques, which provide an unparalleled level of paleoseismic detail. The Sumatran section of the Sunda Megathrust provides one of the most complete seismic records in the world, enabling investigation of multiple earthquake cycles. Robust evidence even suggests events on the scale of 2004 are far more rare, with candidate earlier events occurring from 1290 AD to 1400 AD and from 780 AD to 990 AD, indicating these catastrophic failures operate on systematic millennium-scale cycles. What makes the current Sunda Megathrust situation unprecedented is the sheer duration of the seismic gap. While another event on the scale of the 2004 Andaman rupture is unlikely within the next 100 years, the current understanding for coastal Sumatra, south of that rupture zone, includes the potential for 1 or 2 great earthquakes within the next few decades. The 267-year gap since 1757 represents the longest documented quiescent period in modern seismic network monitoring. We are quite literally in uncharted territory. The warning signs are coming from the most unexpected source: coral reefs. Marine biologists studying the coral microatolls surrounding Simeulue Island began documenting anomalous vertical uplift patterns months before the recent seismic activity. These microscopic shifts in the coral record show systematic vertical movements that precede major megathrust ruptures, effectively providing a natural early warning system for the earthquakes that seismometers can only detect after the fact. The unnerving confirmation came on November the 27th, 2025, when a magnitude 6.6 earthquake struck the offshore subduction zone, damaging buildings on Simeulue, including a mosque and a community health office. The quake's location and timing line up perfectly with the coral warning signals, revealing a systematic reactivation of the exact fault segment that generated the devastating 2004 Indian Ocean tsunami. Historical coral records demonstrate that interseismic deformation patterns often change after the onset of a rupture sequence, and that is exactly what these coral microatolls are now recording prior to the recent seismic events. At sites where historical uplifts are well documented, like those from the 1861 event, the coral record even shows the past uplift was comparable in scale to the 2005 rupture that killed over 1,000 people, confirming these systematic failure progressions can and do repeat. The most alarming revelation from the latest coral data is the presence of time-varying interseismic strain rates that match historical patterns preceding major rupture sequences. Independent GPS data corroborates these coral observations, while advanced hypocenter relocation methods reveal a seismic gap clearly delineated by strongly curved bands of seismicity directly above the subducting Sunda slab. Taken together, these pieces of evidence converge into an alarming picture. The missing earthquake the corals are detecting is no minor tremor. It is a full-scale megathrust failure in the making. Probabilistic seismic hazard assessments published in 2024 forecasted this exact scenario. Using historical earthquake data and state-of-the-art modelling techniques, these studies projected a heightened risk for earthquakes in the range of 6.0 to 8.2 on the moment magnitude scale, with the probability of a major event becoming significant as early as 2026 to 2027. A more devastating event is estimated as likely around 2031, with a specific Gutenberg-Richter frequency magnitude model projecting potential earthquake occurrences and impacts over the coming decades. The official warnings from BMKG emphasize the Sunda Strait and Mentawai Siberut zones as potential seismic gaps that are hundreds of years overdue for significant strain release events, while researchers at Indonesia's National Research and Innovation Agency, BRIN, confirm that specifying exact earthquake dates remains impossible. They openly acknowledge the documented history of catastrophic megathrust events in the region since ancient times. This convergence of hazard indicators becomes truly alarming when combined with the November 2025 magnitude 6.6 earthquake that struck the exact fault section identified in the 2024 probabilistic models as being at highest risk. This particular segment lies directly between the 2004 and 2005 rupture areas and has continued to generate magnitude 7 or greater events as recently as 2002 and 2008, suggesting a pattern of persistent geological instability. Most concerning is the revelation from three-dimensional finite element simulations that the current failure progression matches the stress patterns that drove previous catastrophic rupture cascades. The probabilistic rupture window is no longer a theoretical exercise. It is a systematic failure progression that has already begun. Modern infrastructure amplifies this geological threat to an unprecedented degree. Power system resilience modelling shows an unacceptably high probability that larger megathrust events will trigger tsunamis with potential 16-metre wave heights, capable of utterly devastating regional electrical infrastructure. Alternative tsunami simulations that account for a multi-segment rupture cascade indicate wave heights reaching a devastating 34 metres along the southern coasts of both Sumatra and Java, with average run-ups still exceeding 11 metres along thousands of kilometres of densely populated coastline. The Indonesian archipelago currently faces an infrastructure vulnerability scenario far beyond anything experienced in the pre-industrial 18th century. The nation is encircled by 16 megathrust segments across 6 distinct subduction zones, each with the potential for catastrophic coordinated failure that threatens the stability of critical economic networks throughout Southeast Asia. Submarine fiber optic cables that carry the bulk of internet traffic between Asia and Europe now stretch directly across identified high-risk rupture patches, while major port facilities sit dangerously close to tsunami inundation zones. Economic damage projections for a magnitude 7.8 to 8.2 earthquake event suggest potential losses up to $1.255 billion and significant casualties. But this alarming figure assumes a single major earthquake. The reality of a multi-stage cascading failure event could multiply these economic impacts exponentially as shockwaves ripple through commercial networks that now depend on next-day shipping and just-in-time logistics. Port systems, refineries, and automated container facilities across the Indonesian archipelago currently lack adequate redundancy to withstand prolonged disruptions from sequential megathrust events unfolding over weeks or months. Even more alarming is the dependence of regional power grids on the economic heartland of Java, which sits directly above one of the most prominent seismic gaps, identified through advanced hypocenter relocation techniques. The critical infrastructure supporting over 140 million people is effectively co-located with a major fault segment that experiences an average annual plate convergence of 6 centimeters, with supercycle tectonic behavior operating on 400 to 600 year cycles. In this context, even the low end of the probabilistic rupture window represents an unimaginable catastrophe in the making. The cascade potential of this threat reaches far beyond Indonesia. Megathrust events can generate ocean-wide tsunamis by vertically displacing the seafloor along a subduction interface. Strong shaking can persist for 3 to 5 minutes or more, providing a dangerously long window for tsunami waves to build. With the Sunda Megathrust extending over 5,500 kilometers from Myanmar to the Lesser Sunda Islands, a full-length rupture event could realistically generate tsunami impacts across the entire Indian Ocean basin. Historical evidence suggests such a pan-oceanic cascade scenario may have occurred in the past, with the 1660 Banda Aceh tsunami potentially representing a triggered event repent following a separate megathrust rupture in the Mentawai segment, with Indonesia positioned at the junction of the Indo-Australian, Eurasian and Pacific plates. The potential for cascading ruptures to trigger interaction effects across multiple tectonic boundaries represents a catastrophic scenario beyond the scope of existing disaster response protocols. The economic repercussions of such an event in the modern day are nearly incomprehensible. The Indian Ocean is a true maritime superhighway, with an estimated 25% of global trade volume transiting the Sunda Strait alone. Long-period ground motions from a full-length rupture could trigger liquefaction effects in the marine sediments that now host dozens of submarine oil pipelines and communication cables. Cascading tsunami events, days or weeks apart, could disrupt shipping traffic and port operations for months on end. At an even deeper level, advanced geodynamic modelling suggests that coordinated failures may be driven by deep mantle flow patterns that control anisotropic stress distributions throughout the region. If this hypothesis proves correct, the Sunda Megathrust could represent a symptom of a far larger systematic instability in the tectonic foundation of the entire Indo-Australian basin. With modern supply chain infrastructure forming a globally connected network of networks, a cascading failure event ricocheting across the Sunda Megathrust could send economic shockwaves to every corner of the industrialized world. The Indonesian government isn't taking chances. BMKG has already deployed a network of 39 additional seismographs, 20 accelerographs, and 22 automatic water level monitoring devices in the high-risk Banten and Sunda Strait target zones to detect even the subtlest hints of a major seismic event. Advanced coral microtoll monitoring techniques now provide unprecedented paleoseismic resolution, with colonies essentially serving as living earthquake recorders that can detect vertical land movements months or even years before a major rupture. The alarming confirmation came with the November 27th, 2025 magnitude 6.6 event that damaged buildings on Simulur Island. This was no isolated tremor, it was a direct hit on a fault segment that had been identified by coral uplift patterns months prior. The epicenter location and focal mechanism perfectly align with the coral-derived warnings, a stark reminder that these biological warning systems often outperform our most sophisticated seismic monitoring networks. The same advanced numerical models that predicted the heightened rupture risk from 2026 to 2027 are now using high-performance computing resources to match the active deformation patterns to specific fault geometries and stress regimes. The systematic nature of the threat is becoming undeniable. Stress transfer simulations clearly show how a cascading failure event could unfold across the segmented Sunda Megathrust, with a magnitude 8.0 plus event near the Mentawai Islands, potentially triggering a second event in the Sunda Strait, and so on until the entire fault has ruptured from end to end. This is the true power of the Earth system models, underpinning our 2025 risk projections. They do not just estimate the timing and magnitude of a single earthquake, they anticipate the synergistic effects of a systematically unzipping subduction zone, with the same approach now being deployed to assess earthquake and tsunami interactions, landslide cascades, and volcanic flank collapse scenarios around the globe. The age of geological threat anticipation has truly arrived. But for the millions of people living along the Sunda Megathrust, anticipation alone will not be enough. Dr. Daryono's dire warning that the Mentawai and Sunda Strait segments are hundreds of years overdue for a major rupture is not hyperbole. It is a mathematically rigorous statement, backed by models that have proven their predictive power time and again. The BRIN team is clear that the precise timing of such an event remains impossible to specify, and that scientific reality will come as little comfort to those now living in the shadow of a magnitude 9.0 megaquake. In the end, perhaps the most sobering warning comes not from the experts, but from the corals themselves. If these sensitive biological indicators have indeed detected the first signs of a major Sunda Megathrust rupture after 267 years of unnerving silence, then we may be witnessing the start of a catastrophic sequence with the potential to reshape the lives of over 500 million people in a matter of moments. When a single subduction zone can trigger 30-meter tsunamis across an entire ocean basin, the word overdue should strike fear into the heart of anyone paying attention. This is Earth Attacks, where science meets planetary survival. Like and subscribe to keep up with the latest on the Sunda Megathrust, and stay alert for more updates as this urgent situation unfolds.